Today, SuperMUC, an IBM hot water-cooled supercomputer built for the Leibniz Supercomputing Center in Germany, has been named one of the most powerful in the world. The official results were reported yesterday during the International Supercomputing Conference in Hamburg. The massive IBM iDataplex supercomputer is 3 petaflops with more than 18,000 processors, yet it consumes 40% less energy than a comparable air-cooled machine. SuperMUC achieves these remarkable energy savings by employing an innovative cooling technology, which is inspired by the human circulatory system. Similar to how blood and oxygen are delivered throughout the body, microchannel liquid coolers transport water directly to the processors and then carry away the heat. The heat is then transported to a heat exchanger, where it can then be used to provide heat for the buildings. Herbert Huber from the Leibniz Supercomputing Center explains why the supercomputer is so important.
Germany is very greenish, so to say. So energy and power awareness is a crucial aspect in Germany. IBM came up with a direct liquid cooled system, so with a completely different cooling technology, which allows us to operate our supercomputer the whole year without any chiller, without any compressor. We can save up to €1 million per year, only because of this new cooling and system packaging technology.
SuperMUC is based on the IBM Aquasar supercomputer that was built for ETH Zurich in 2010. Both computers are significant milestones in a water-cooled computing roadmap for IBM that can be traced back to the 1960s. IBM scientist Bruno Michel explains.
In the future, we will reduce the size of the system by another factor of 10 for the next 5 years. And as time goes by, for each 5 years, we need to reduce it another factor of 10, which means then eventually a millionfold reduction of SuperMUC so that it fits into one box, like one PC box. The entire system that's currently many thousands of cubic meters into an entire PC box. And that will increase the efficiency of the system by a large factor.
Now that SuperMUC is operational, it will be available for scientists across Europe to explore a wide spectrum of research. Hans-Peter Bungay from the University of Munich comments.
We want to use the SuperMUC to figure out what causes earthquakes. What SuperMUC will allow us is probably an order of magnitude better understanding at a level that had not been dreamt before 20 years ago. When I heard about the size of the machine, I realized that the length scale and time scale problems would for the first time be really addressable with that machine.
SuperMUC will be officially inaugurated in July at the Leibniz Supercomputing Center in front of hundreds of guests. This is Anne-Marie Cromack reporting.
Repulsion is really strong when you get closer to it.
Just like any other motor, past a certain threshold.
Energy efficient computing there's an image which goes along with computing, and mostly it's still at this level. Big machines crunching away, consuming megawatts, and there's a big weather prediction computer which is over there in Exeter at the moment in the weather centres. And are they the major issue about energy consumption in computing that we need to be considering these days? Or is it these? Laptop machines, they're all over the place, consume a couple of 100 watts each. They're not the most energy efficient things in the world, but there is an awful lot of them. And so the cumulative energy that they use is quite significant. But these are, in many respects, traditional computers. They're a box that doesn't do anything until you tell it what to do. It just sort of sits there. Then we start to move into the other area of computing, which is starting to become relevant. And I suppose this is where the prop comes in. A computer like that, they're now talking about billions of these existing in the world. And although they consume only the order of a watt or so of power, then you're talking about a huge amount of power overall. Now, the question is, of course, is something like this a computer? Now, today, we do find the computers everywhere. Now, to you, this shouldn't be too surprising. But to an awful lot of people, most people don't think of an awful lot of these things as computers at all. All right, this one might be, but a camera or a game, an electronic game, or a printer or a washing machine, can they also be computers? And that, of course, ignores the ones that they don't know anything about, yet use all the time. Congestion charge if you're up in London. Your car is heavily electronified. That's a word I've come across now. It's an official word, apparently. Robots, medical, credit cards, and the whole business of financial transactions. Of course, power systems and the management of those, including communications with satellites, transportation. All of these things are supported by technology which is, one way or another, electronic systems and computers. The cup of tea, incidentally, I put there because I like the logistics aspect of this. A cup of tea is pretty well valueless, and yet it involves pure water, it involves tea brought from all around the world, it involves ceramics and the ability to create them, and the biscuit, of course. All of that into something which is so casual is really only supported by the advanced logistics systems which are supported by electronic systems, of course. So we're now talking about hundreds of billions of computers, but most of which most people don't think of as computers at all. And whilst they may only be consuming milliwatts of power, the combined effort, the combined total of that is a very significant factor. It's bringing embedded intelligence to the consumer, which has changed the face of computing again. So our 21st century world has 7 billion population, large percentage of which has historically not been in a position to make use of a lot of technology, but is rapidly changing that. Its growth rate at 2% per annum is a significant number when you're talking 77 billion rather, and the life expectancy is going up across the world, so not just seeing that number increasing due to birth rate and improved health and so on, we're also seeing it the persistence of people because of the availability of food and so on. And pretty well all of them want some new electronic system in their lives. Both visibly, they want to buy the smartphones, but they also want to have the support which goes along with logistics of all of the other good stuff that we have in our lives in the West, and they tend not to have so much in other parts. Now, it's markets which have been the drivers of the main evolutions of the computer. And if you look at these, they're quite interesting because the mainframe, the numbers involved in mainframes, they kicked off in about 1960, 1970, but you're not into the tens. Worldwide, these are low numbers. The first era took it into mini computers, personal computers, desktop, mobile internet, and Internet of Things. Everybody knows what the Internet of Things is, don't they? No, they don't. Nobody knows what the Internet of Things is. They only know that it's a very large number. And so we've got this. Each one of these increments is a very large increase in, let's say, shipped computer systems. but it's not necessarily known what they're going to be used for. So the Internet of Things, mobile internet, nobody really knew what form factor the mobile internet was going to happen in. And several people tried with their products, but it was only eventually really when Apple came up with the iPad that suddenly it became fashionable. This is the form of a computer that the consumer wanted to buy. You notice that there's a dip in the desktop, because these people have been using desktop machines. They suddenly realized that actually what they wanted to use it for was better catered for by the next evolution development, and that will happen, of course, on the mobile internet. There will be declines in the sales of the tablet devices as a result of some new features which emerge out of this much larger connected community associated with the Internet of Things. 2%, a figure I have, unfortunately I've lost the reference for it, but I know it's in there somewhere. 2% of our current energy usage, this was based on a 2011 figure from America, goes on powering electronics. Now, if you consider that most of the electronic systems around today are sort of computerized, many of them are not. Certainly in the next few years they will all be computers, embedded or application machines. But the trend will easily lend us to a situation where 20% of the energy consumed by the human race will actually be going on powering the electronic systems that we're creating. So it certainly matters. Now, is it real? How much do we know about the Internet of Things? As I say, we don't know a great deal about it, but these are some of the stuff which comes out of our marketing slides. And here is the cumulative total, sorry, that's the actual shipped devices, because you can see there's a dip in it. But we have 40 billion ARM CPU systems out there at the moment. 40 billion. There's only 50 million desktop PCs in the world today, just to give you an idea. This line over here is a very real line which our marketing guys have done from not just predictions, so it's not just the back of an envelope sketch, it is using the information that they know about the products which are being developed, the markets that those guys anticipate getting, and including a factor for the fact that they are not always going to achieve what they plan to achieve. There's a pretty good roadmap to 150 billion CPUs out there by 2020. So that's around 4 times the number that we've shipped already so far. So it's pretty big and it's happening. The interesting little thing that came up as well is that we knew we had penetration, but we didn't know how much, and Gartner came up with a figure which quite surprised us actually, that 75% of the things that are connected to the internet are ARM powered. So this is again a staggering thing. The internet is almost a delivery vehicle for our products. So we all know about Moore's Law, and there's two sides to this, but we'll ignore the red line for the moment. The black line, blue line, really illustrates a factor that we know, this factor of 2, which is every 18 months to 24 months, of the factor of 2 growth in the number of transistors and devices which are available in an integrated circuit. What you might wonder is why I've used data which is dated 1999. So ARM was started there when the typical integrated circuit was about 1 million transistors. And you're now looking at a situation where there's 20 billion transistors that you can get on an integrated circuit for around £5, memory device albeit. That's 20,000 times more capacity in that silicon than when we started. And it's a very real factor, because of course this means that the design methodologies that were applicable for 1 million transistors on an integrated circuit cannot be remotely applicable for 20 billion transistors. It's a much bigger task altogether, and synthesis and reuse have come in as a major factor to actually deliver that. This has meant that the approaches that we're using for designing these products are less efficient. We're getting the products out, but we're doing it in a less optimized way. When you've only got 1 million transistors, let's say, you think about those transistors an awful lot before you place them. When you've got 1 billion transistors, you put them down. You just chuck them down. Let's get it done. What matters is getting the product out, getting it working. And that produces inefficient design, but functional design. So, returning to the computer theme, a machine for computing. But if you look now in this wide sphere of computing, we know that computing is not just about digital computing. It's about processing information, processing numerated phenomena, and producing some useful output from it by just straightforward manipulation. State and time have always been factors in this, although not always obvious. And it can include abstract phenomena as well as real physical phenomena. But essentially it's used, you create a model, and you exercise that model to predict something about the future. That's really what we're doing. We're doing it with an iPhone, and we're doing it with weather forecast, we're doing it with an engine management system. You don't have to do that with digital technology. You can do it with all sorts of technologies. And if you go back to the first computers, and this one is 87 BC, a mechanical thing found like this in the Mediterranean. Took a lot of work to work out actually what it was, because it was by far the first mechanical machine. Mechanical machine. These are gears and cogs, and yet the whole thing was sort of enmeshed in a calcated block, so you could really hardly tell what was there anymore. It was all produced by hand. There was no gear cutting machines or anything else like that, and even the production of metals in those days was a difficult thing to do. It's interesting to think about that, because what we really have here is an engineer, who probably didn't call himself an engineer because that was a very much more modern term, set about taking the technology that he had available to produce a machine which was going to create a model of something which is useful to know. And it was for predicting the position of the stars, helping with navigation. Later on, by 1700, the production of metals was not a major problem anymore, not to that guy. You could go out and you could buy metal. And so the orrery is probably the first serious computer which is available in any quantity, but it is still mechanical, of course. Babbage's difference engine, this was nice. 1837, it was still not possible to make this thing, because although they had the metals very easily, they didn't have the precision engineering. They couldn't produce the gears and the cogs as accurately as they needed to do. So it wasn't actually created until 2000. Because it's only then, using modern numeric controlled milling machines, that they were able to produce gears which were sufficiently accurate to make this machine possible. So here was a computer that was designed on a technology that it wasn't actually possible to make. Now, we're all used to, in an engineering sense, designing things which are impossible to make. But what we're realizing here is an engineer is separated from a scientist in that sense, because an engineer, his success is determined by his ability to produce something that does work from the technology which is available, whereas a scientist can have the luxury of just finding out. The Enigma machine for data encryption in the war. Very much a mechanical machine, had to work, electromechanical. But Colossus was interesting because this was the first electronic computer essentially to do the decryption part of that. At this point the computation activity had moved to valves. You can call it electronics, it was to do with electrons, definitely. Baby, the first general purpose computer, 1947, this is not so long ago. Now, you can look at me, I've got grey hair, I am definitely now in the class of humanity called older. But I was born in 1949, so this is 2 years before I was born. And then, of course, there is signal processing. And in a similar era, you've got the first radios running through to, well, okay, it's not the latest, but it is at least a DAB radio these days, and essentially doing the same thing. They're taking a signal from the air, they're manipulating it and massaging it, and they're making it available in a way which is suitable for coupling to a human ear. So it's a simple process. Okay, the earliest ones didn't have this basic architecture, but most of the radios, once you started to move into the electronic domain, have this architecture. These blocks are still in there, and the equations that are effectively being done in each one of these blocks are still the same. I mean, the good news about these is it's close enough technology. I mean, you don't really mind if your radio is a little bit quieter or a little bit louder than your next door neighbour's one, because you twiddle the volume control. If it drifts a little bit, it's usually not a problem. You have the knob on there, you're able to retune it. Sometimes one of them flattened the battery a little bit faster than the other. It didn't matter. So in the early days of radio, there was more variability. Come on. But this is like the first or the earlier implementations of that architecture using valve technology. Some of you will maybe Guido and I certainly remember valves. I guess that's probably everybody in the room in that basis. But when I was an apprentice, when I left school, I was working on valve equipment. It's actually very similar to transistors, just the bit bigger, that's all. But the equations were the same. Then, of course, the transistor implementation. Again, the blocks in there, a few more transistors, because actually transistors don't have as much gain as valves, so you couldn't do quite as much. Also, transistors are 3-terminal devices. Valves, you could have up to 5 terminals on them, so you were able to do quite a bit of clever circuitry in valve days. But in transistors were cheap. You could put more of them in. It wasn't a problem. And so, we started to get into the era of doing things in discrete blocks rather than trying to combine them. And then, of course, today, radio as a component, you don't know what's inside that block. You only know that conceptually it's got an antenna in and it's got an audio out and it's doing the same function blocks inside. But whether it's done in digital or whether it's done in analog, or which parts of it are done in digital and which parts of it are done in analog, you don't know. But it nevertheless is computation. So where is computers in all of this then? Computing is in all of it. And computing, if you look at a modern computer, then you'll find that inside it are pretty well all traces of all of those computing technologies today. It is creating useful output from input, and the way that this is done is architecture. Now, architecture is probably one of the least appreciated skills that we have to go through here. It's the most important product decision, without a doubt, because you have to live with the consequences of those architectural decisions for the lifetime of the product. If you get it wrong, no matter what else goes in and happens with the rest of that as a product design, if you get it wrong, it doesn't work. It's not as effective as your competitor or anything else like that. And yet it's the thing that we tend not to focus on when we're doing design. Design is electronics, or it's software, or whatever. It's the bit that we're interested in. But actually what we have to remember is it's the system which ultimately sells product, and it's the product which ultimately funds all of the activities that are in its creation. So hardware, software, digital analog, optics, graphene, mechanics, steam, etc. can all form parts of modern electronic products. I mean, petrol is still part of the internal combustion engine. A car is increasingly an electronic system. So petrol is in the loop. You don't forget that. You tend to think of it as something else. So I've rehashed Moore's law a little bit, and I said that Moore's law is really only a continuation of what's been in reality happening for a very long time. There have been technologies, emergent technologies, which have enabled a radically new way of achieving a functionality that you've previously been doing with bits of wood, perhaps. Metal makes it much better. And then we have mechanical, then we have electrical things, systems based around electric motors, and relatively big, powerful, chunky things, microelectronics and electronic systems is where we're headed today. The good news from my point of view is this was my era, really, and from your point of view, this is yours. So I can walk away at this point, or fairly soon, and say, okay, I did okay, now you guys take over and you take the next technology steps, whatever they mean, because you're going to have to look at the technologies that are going to be available and the ones which are available today, and you're going to have to use those to deliver a product, because the market requires a product. And if your business is in supplying a customer, if you fail to supply that customer, it's a hard world out there. You're out of business. And the people who do manage to get the formula right, architecture it correctly and implement it with some technology which is possible to create, then they're the ones who get the market, and you're all of a sudden out of it. Now, it tends not to be popular to express it, but actually it's a fairly well part of our capitalist model, that businesses grow, they plateau, and they die. All businesses die. They die at some stage. So ARM is sitting here. We're very popular and very confident and very well connected to the market today, but we don't count our chickens. We know that we have to work very hard to keep that position. And in many respects, we know that sooner or later we're going to lose it. So, computing in a cool icon. A lot of architecture inside a smartphone. I'm not going to break it down in detail for you, draw circles around it or anything else like that, but you can look at this. This is just something which I pulled off the web. I can't remember whose smartphone it is at the moment, but you can see we've got microphones here, we've got RF parts here. Look how many RF channels there are. 1, 2, 3, 4 RFs, 5, 6, 7 RF systems in something like that. Is it the most effective way to create it as 5 RF systems, or would it be better as 1? Well, those are the sort of architectural decisions that somebody has to make. Audio here, audio amplifiers, should they be Class A, Class B, Class C, or Class D? All matter. Class D is most power efficient, but actually most inclined to die. So if reliability is important to you, it's also likely to create interference, and interference might be a problem with the radio network. So all of those are architectural decisions. You get it right, you've got a successful product. Get it wrong, you're out of business. Most people don't really know what's inside a smartphone. They kind of still believe, and that's even people in engineering working on the chips, they still kind of believe that there is one chip in a smartphone. Well, actually there is 20 chips inside an iPhone. That's a lot of silicon, actually, and it comes from all sorts of companies all around the world specializing in different things. So anybody who tells you that these products come from, let's say, as it says on the back, designed in America, manufactured in China, is just making too gross a simplification to be true. All of these chips, they didn't grow on trees. They all had to be designed by somebody, and they had to compete with other chips to go on that printed circuit board. Because if somebody has got a MEMS device here for, let's say, working out the magnetic compass, or maybe the accelerometers, they've bought AKM device there. They could have bought an ST Micro device there. Now, the reason why they didn't buy the ST Micro one, I guess, was because the ST Micro one didn't have as much performance as was required. That means that when you build a system like this, ST Micro is in competition with AKM, and the thing that they have as a tool is the quality of their design, the architecture of the design, the implementation of the design, the cost and the quality of the thing that they were able to ship. That's one side of the board. There's another side. There's a challenge. How do you make a board with so many components on both sides of it, such that the components don't fall off when you try and solder the ones on the other side? A lot of stuff. Inside the A4, which is the circular fellow down the bottom there, but here is a processor which is of a similar era. This is the NVIDIA Tegra 3. This one's got 1, 2, 3, 4, 5, 6 arms in it that you can't, one of which you can't see. Just to give you an idea of how many arms you're using. And people are now using arms a bit like we're using transistors in that radio. It doesn't matter how efficient they are, they're cheap enough. We've got so much silicon here, we don't know what to do with it. Let's just put down another computing block, and if it makes sense to put it in a separate computer rather than try and integrate the software in one kind of homogeneous lump, then architecturally it matters more to get the product out, it matters more that the functions are reliable than it is in any way ideal. I've got another presentation about productivity in this area, and actually software as such moving into products like this is really a productivity support vehicle. Now, to give you an idea of the level of sophistication, there's 1 billion transistors, and you go down and you go down and you eventually find there really are transistors at the bottom. There's 3 of them there. Look at all of the wiring necessary to locate just 3 transistors, and you've got 1 billion in that integrated circuit. Do we pay that much detailed attention to wiring up those transistors? Well, actually we do a pretty good job, but is it an optimized solution? Hardly likely. There's a lot of slack in this. It's becoming an issue of packaging. It's wonderful to think what you can do inside something like this, but actually the technology is not dominated by microelectronics. Look at all of those other things which you need to know to get that inside the box. How many of those things could you cross off and still end up with an iPhone which is working? And the answer is not many, actually. You take the displays out, it's not really going to look very good as an iPhone. If you can't assemble it, and let's face it, you're going to have to use robotized assembly here, because these components are pretty small, very precisely located, and you need to have a yield at the end of the day. It's got to work. Not only have you got to be able to produce one of these, you've got to be able to produce 1 billion of them, and not have yields which are so bad that you can't afford to make it. So there's a lot of technologies inside this. So I've already said architecture is the most important thing, but you also have the effect that architecture is the cumulative effect as well, because designs are almost never done on a clean sheet of paper these days. You always start with the product which you already have, and you amend it and you modify it and you tighten the integration and you improve the performance of. It's always incremental. It's evolution. And the measure of a good architecture tends to be the one that survives. You look at all of the large churches around this country, and that you marvel at how well they've put together these stone structures with tremendously filigree stonework holding up various parts of the roof and the walls and so on. And you think, how did they calculate that? Well, the answer is, of course, they did calculate it, sort of, but the ones that survived are the ones that got it right. There was a lot of churches that were built that didn't survive. They did fall down. Go and have a look at Malmesbury, incidentally. That's a cathedral, or what was left of a cathedral. It's about 1/5 of the size of the original building, as the bits fell down, and Malmesbury is not an earthquake zone. You have to think system. Components in the system can have poor performance. This does relate to power, because using a poor performing component can still give you overall better system results. So it may be, if you're designing purely for power efficiency, for example, you'd use a component which was the lowest power solution. On the other hand, within a system, that one may have more control, and in the system context it's easier to turn it off, for example. So the system aspects matter, not just the individual performance of components. Additional to the pure architectural models, you also have business models. The cost of ownership. How much is it going to cost to buy this? The time to market, the history, the availability, aesthetics. People don't buy an iPhone entirely for the technology which is inside it, and in fact most people don't buy it for the technology at all. They buy it for the functionality. And if you've got a phone which is not quite as square and as crisp, carved out of solid obsidian, a volcanic glass like the iPhone is, then people will tend not to buy it. Not for a technical reason, but for an aesthetic reason. So aesthetics are part of this architecture. Technology is in there, but reuse is in there too. More than 90%, 99% of a product these days is reused from its predecessor.
You talk about the design inside, not the material.
Well, the design inside, but frequently the chips themselves are reused. The iPhone various histories will still be using some of the same display technology on the outside. They're still using the same finger contact detection technology. So it's a lot of functionality is the same. The software, large parts of it are going to transfer from one design to the other. And the reason that happens actually is that that's what software does. It is easily reusable. It was essentially designed to do that, so the good news is it succeeds in doing it. Oh, the last point on that one. Is a significant one. Functionality is assumed. You're expected to make this work. So your job, if you do your job properly, is unnoticeable because you've just made something that works. If it doesn't work, then it is noticeable because the business usually goes out of business fairly quickly these days. But it's unappreciated. It will remain that way. Engineering is in a corner, but we have to take the responsibility for making sure that people, ordinary people, become more aware of the roles that we play, because it may not be very noticeable, but it is very important. So getting more back to power philosophy, it's hardware that dissipates power. This is undoubtedly true. No matter how many lines of software code you write, it doesn't dissipate any energy at all. It's only when you try to execute it that energy starts to happen. But it really points out that software doesn't exist on its own, and neither does hardware anymore. You could make a system a little while ago which had no software in it, but if you can argue that an analog component, let's say an amplifier, an IF amplifier or something like that, is actually a computation engine with a fixed instruction. It's configured and it runs and it's complete in itself. Whereas you've got the more general purpose ones, which are an ALU with an instruction engine. Then that's the general purpose solution, and the general purpose solution is not as optimal as the optimized one. But software tells hardware to dissipate energy. Hardware can do it on its own, but software helps it. And quite literally these days, it's possible to make chips melt under software control. So software which is not aware of the power consequences of its action can actually destruct the chip. It didn't used to be possible to do that. CMOS used to be self-protecting. It isn't anymore. So a rule must always be on here: always make your computer hardware as activity dependent as possible. It seems a little bit of a strange thing to say, but you aim for zero activity equals zero power. This has not been the way that computers have been designed traditionally. A lot of computers aim for flat power consumption, and the reason for that is flat means less noise, and noise means the circuits are likely to stay working. The problem is that flat means it's dissipating that power whether it's computing something useful or not. What we're doing here is saying when it's doing something useful, we accept the fact that it's going to dissipate power, but when it stops doing something useful, it's not going to dissipate power. So overall, these computers sit around doing nothing most of the time. If you've got a great big mainframe, then arguably it's going to spend a lot of time doing something. So it's less of a problem in the big machines as it is in the small one. The other one is make the operating systems and the applications aware of the power. Again, it seems a little bit perhaps obvious, but if the operating system, if the software which is causing hardware to dissipate power, if it's unaware of the power that it's creating, then there's nothing it can do about moderating it. And indeed, if there's no levers, no adjustments that it can make, then it also is unaware of that. So you need to have indicators and you need to have levers in the system which are not to do with functionality. So these are non-functional constraints, non-functional requirements which have to be incorporated into the box. And that's a bit of a break with tradition, because The whole philosophy of software in the early days was about isolation. You didn't need to know about the platform that it was going to be running on. In this world, you've got to know about it. But it's think system, again, it's how the box performs, not how the components. So there's 3 elements of power management that we use in this area. I'll tell you about them. The core management for the processors and the peripheral circuits, variable and gated clock domains. These are ways to achieve that objective of zero power associated with zero activity. Variable and switch power domains. None of these are functional in the sense that they add anything to the performance of the box, except in their power domain. It just makes the design much more complicated. To switch the clocks means that you've got to have parts of the circuit which don't mind that the clock speed isn't constant, that don't mind if the power is going to go up and down. They've still got to function correctly. That just adds complication, but the benefits are huge. We've got to have indicators and levers, but we also have to have the software to recognize that. Traditionally, operating systems were not concerned about that, and so building links into this from the operating systems for the likes of the smartphones has become a major activity, not just for us but also for our customers. This is the very useful thing to remember, that the power dissipation is actually proportional to C and F, but is actually square law proportion to the voltage. And so trimming the processor performance so that it only just has enough performance to do what's required is a very sensible thing to do from a power point of view. That also maximizes the gain that comes out of that. And of course, it doesn't just apply to the chips. There's a lot of chips on that Tegra chip that I showed you earlier. A lot of CPUs on that Tegra chip I showed you earlier. There's a lot of other stuff on there too. The energy which is being consumed in the system is not just being consumed by the CPU. So it's important to be able to apply that methodology across the design as a whole. And that's not easy when you're talking about a billion chips, so we need a billion gates. So we need a methodology. And we need all of these things like retention latches and level shifters and power switches to make viable all of the techniques that I was talking about. You've possibly come across parallelism, but you may not have come across the reason for it. There's these 2 guys, Amdahl and Gustafsson, really, who I don't think they set about to establish these 2 areas, but it is the ground that came about. If you start off with one arbitrarily big processor, which has an equivalent capacitance, it's got a working voltage and it's clocked at a certain frequency. If you split that processor into 2 blocks, each running at half the frequency, then you end up with a block which is bigger, so it's 2.2 times, so 10% up on area, but actually consumes rather less than half of the power. And it's a linear equation which determines this, so 4 times is 0.2, and so it goes. So there's a significant amount of power efficiency to be made out of parallelism, if you can do it. Because you don't need the voltage to be as high, because it's now operating at a lower frequency. So you lower voltage because you don't need the higher frequency. So Amdahl and Gustafsson come into conflict here, because Amdahl basically says this is a good plan, but actually you can't extract much parallelism out of effectively software, reuse software, which has been written linearly. And in fact, if you look at the quad-core type processors which you find in average PCs, they're limited to quad-core primarily because they need to try and extract parallelism out of that linear code. The reality is you can't do much more than about 2.5. So even with your quad core, one of the cores is hardly used at all, and one of them is only used about 50% of the time. So it's not something which scales terribly well. But Gustafsson took the other approach, and he said if you were looking at applications, you're writing your code again from scratch, are there some applications where you could gain hugely out of parallelism? And the answer is yes. if you look at the data processing type computation, the sort of stuff associated with that radio or image generation and support, then that activity is naturally very highly parallelizable. And so the idea of using a GPU is really in support of Gustafson's observations in this area, that GPUs are SIMD, single instruction multiple data. You have a single instruction because you're working on all of the data in the same way, and you just have a vast array of data because the application is naturally associated with essentially array processing. So the real system then would need to be a combination of the two. So not surprisingly, we're going to start to see some novel architectures. So the actual improvements that you get, though, are going to be application specific. So if you have an application which doesn't require a lot of digital signal processing, then having a DSP block in there is only going to produce a result which is less energy efficient. The other thing to bear in mind is that moving data around is also a significant energy consumer these days. In fact, it's looking like it's on a par with all of the other energy consumption at the moment. It's difficult to actually pin this down because you're talking about moving data and it doesn't actually show when you look under an electron microscope. But the consequences of stopping moving things moving do give you some idea of the amount of energy which is going that way. But it's avoid moving data. There's this equation which is pretty well, let's say, indicative. Nobody is owning it to the point where they don't actually know how steeply dependent it is on distance. I'm inclined to think it's possibly even fourth order. Certainly moving data short distances is much better than moving data long distances from an energy point of view. It does bring about an architectural choice, though, bringing the processing to the data. What the hell does that mean? Instead of having a processor in the middle and data brought to it to be processed, what it started to say is, let's move the processing all around the place, which is actually quite consistent with the Amdahl and Gustafson approach. Gustafson gives you potentially a better opportunity for spreading it around. But basically, doing things in one place isn't the logical thing to do if you're doing it for energy efficiency. Caching is good because it brings the stuff from the memory distant and it brings it to a local area to be worked on. But write back is better than write through. You don't want to do any more writes than you have to, and you certainly don't want to write to a local memory and to a distant memory just in case. So a more sophisticated cache controller is the result, however. But you've got lots of gates, got lots of transistors, so that's not necessarily that much of a problem. And local working memory is good, so think of that as a software cache. The arrangement of your data matters. This is kind of novel because the architecture of the system now is not just the architecture of the things that you can see, it's also the architecture of the stuff that you can't see. How you organize your memory. So we'll do a little bit of ARM advertising because it's in there, but it's really more to point out how we have incorporated those lessons into our products. So ARM makes a processor which goes into smartphones. Actually, that's the sort of top level message that most of the investors believe. There's actually 24 cores in our current processor family aimed at different applications, different domains. We've got the general purpose processors over here, and you've got the DSP processors over there. The DSP processors are naturally multi-core products. The general purpose processors are naturally single core processors. Just need to see what else is on that slide. Oh yeah. Choosing the horse for the course then. You've got 24 processors. Why have you got so many? Well, the answer is you want to choose the processor which is most closely mapped to your application because that's most power efficient. So you need to have a range of processors which can be scaled if necessary, but certainly to look at the major parts of the activity which is going on in your application and make sure that they're not over-designed for that capability. So here's an A15, which is the top of the range processor. It's got a fair degree of parallelism inside itself, lots of caches, lots of FPUs. It's a heavy-duty machine, sophisticated memory management to allow it to support lots of applications. Here's the Mali DSP set. It's got a scalable core, much simpler looking on the outside, but it is actually a SIMD machine, so it's only got a fairly tight instruction loop, and it's got this vast stability because the decodes from each one of the instructions is going to be rippled out across all of the machines to do it on the largest body of data at the same time. But to put some sort of scale on it, here's the smallest one. This is the M0. 15,000 transistors in the M0, 50 million in the big ones. That's a lot of scale difference between those two. And that's why we actually need so many different ones, is to get the application point right. And it matters, therefore, from an architectural point of view. So we've already been using heterogeneous multi-core systems for some time. Heterogeneous means different. So we've got the Mali GPU and the Cortex CPU. Now, not too radical that, because most people think of these days as a processor as having a GPU and a DSP on the same chip. But of course, in our earlier history, some of the chips that we produced only had a CPU in it. That was all that the applications were requiring at the time. But this is symmetric multiprocessing. Sorry, heterogeneous multiprocessing. And the reason it's multiprocessing is the application that it's providing, whatever it is unified. It's using these resources, but what we're actually doing is processing data from the input into something useful from the output. So the task that it's achieving is still essentially a single task, but it's using parallel resources to achieve it. Now, this one is naturally Gustafsson, because that one, even the first Mali was a quad core. It wasn't scalable, but it was a quad core in itself. And this little fella over here, well, because we've got CPUs and we can use them for all sorts of things, then the power manager is a CPU on its own. Why not? We could put it as a task on this one, but then we'd have to have an operating system on this one, and we'd have to make sure that the operating system never crashed, because the power manager had to continue to work properly. So it was easier overall, rather than trying to combine the tasks, to keep that one as a simple separate task. It's just a few thousand gates over in one corner. It's an architectural decision. Moving on, the general purpose cores started to gain multi-core implementation. So in the A9 we were able to produce up to 4 cores in a block. The Mali, of course, is still in there. We still have the power manager. But what we're seeing now is Amdahl coming in. So Amdahl is not going to take that number up to the very highest orders that it's possible to take this, but it is nevertheless going to gain some benefit out of doing it. We're starting to improve the cache coherency, bringing in second level caching to avoid moving data any large distances. But we're also starting to see now clusters of clusters. So here's a potential 4 cluster and another potential 4 cluster, isolated from one another. So that's moving the computation to the data. So rather than try and do all the computation in one block, split the blocks. Energy efficiency. So a typical CPU in an embedded system these days, this is an example design that when we sell our products to people who are designing chips like this, we give them these example designs as part of that package. They throw away parts and they put more in there, and they connect what they want to connect onto it, and they use them in 2s and 3s. But this is an example of something which will have been used in all probability with the likes of the chip that I showed you the picture of earlier, and probably equally with the Apple one, if we would admit to it. It's got 2 clusters of 2 CPUs. It's got a Mali processor here with 1, 2, 3, 4, 5 parallel processors on board. There's also a DMA controller, which is smart, a LCD controller, which is smart, a memory controller, which is smart. So they've got processors in them, because why not? You've got processors. It's easy to make them sophisticated. So we've got 4A9, 4 Mali frag processors, 1 Mali vector processor. There's also an MPEG engine. There was typically 10 processors, and that's in the A9 family. We're now currently at the A15, so we're 2 years further down the road on that. So you can now see the sort of architectural, in some ways you consider it a mess, because the traditional view of a computer was effectively one ALU in the middle, an instruction engine around the outside to fetch data and interpret the instructions and apply it to the ALU, and then a set of registers for putting the intermediate results. It was a very simple, a very clean model. This has got a lot more sophisticated, a lot more complicated, and a lot more difficult to manage, but at the same time capable of delivering a lot more. Raw performance, but also power efficiency. So a different illustration, but this is now the A15 processor, which is the latest. Each one of those is a quad-core processor. So 1, 2, 3, 4 of them. We've got DSP engines there in their multiple forms. Level 2 caches. Each one of these has got level 1 cache inside it. Doesn't show. You also have the cache coherent network. This network which joins things together. It matters too, because moving data means moving data through some sort of communication network. That changed from being a bus, literally a lot of wires connected to peripherals, to being a lot of point-to-point connections. A lot of point-to-point connections basically says you need to know what that processor quad-core is ever capable of talking to, because you're going to actually wire it in. You're not going to allow it to connect to things which were not originally specified in the architecture. So this becomes a huge multiplexing matrix, sparse matrix. So it's not possible to connect everything to everything else. But it is actually a very power efficient way of doing it. Not quite as restrictive as it sounds. And of course, it's not just a case of clever hardware. You've got to have the development environments to go along with it, because sophisticated as your hardware may be, if you don't have the development environments, you can't make a product. A product is not clever hardware, neither is it clever software. It's the clever way that they work together. Big Little Processing, the new kid on the block. This is the idea which starts that we could optimize processors for performance or for power efficiency. And we can put them together in clusters, and then we can migrate the tasks between those processors. It doesn't make sense if you've got a room-sized computer, but if you've got a computer like this, then you can use a Cortex A7, which is implemented as a tiny but identical processor to this one. This one has a much deeper pipeline, is capable of being clocked much faster, is capable of highest performance, but actually a lot of the time your processor is not doing very much. So if you can migrate the process onto the smaller core, which is more power efficient, then it makes a lot of sense to do so. This is a very popular thing these days. So we're seeing CPU migration, where the actual tasks are swapped under effectively kernel control. But we're also seeing virtualization on chip. This is something that was previously only done inside big data warehouses. It allows you to think not in terms of the processes running on a machine, but the processes running on a virtual machine, and then separately the operating system is capable of moving them to the most power efficient or performance efficient domains which are applicable. And it's not just there, we're seeing it moving into the server space. Not all servers are the same. This one is one that's come out of HP's Moonshot product. They're realizing that servers are not always used at 100% all of the time, and some of the applications only serve data, they don't actually fetch much data. And so with the knowledge of the kind of application that you're going to be using it for, so I'll give you the example of what do they call it, the BBC TV delivery system. The quantity of servers you need is going to be tremendously variable on the number of people who are watching a program at any particular time. The attraction of this is you can turn off your server progressively. All of those servers which aren't in use, turn them off. It's an architecture which is not aimed at fetching in data, sorting data and outputting data. It's essentially taking a file which is already in existence and serving it. It's a very limited kind of server, but nevertheless it's matching it to the application. So the lessons apply at bigger levels. And they apply equally in the sense of the Barcelona supercomputer here, where they've realized that processing data is one thing, but actually if you can process information, it's much better. So they're minimizing the data which is moving around by actually consolidating it rather than using it in its in its raw form. I'm very much aware of running out of time here, so I'm not going to spend time talking about that. Last but one slide anyway, just to think about society's challenges, because people have got the idea that you as engineers are going to fix society's challenges. You're not. I've told you that our technology is going to consume more power. It's going to take the 2% to 20% if we're not very careful. What we're doing here by being energy efficient is we're taking the 2% and making it only 10%. We will improve the energy efficiency of the systems that we produce, but we're not going to solve the problem. If there is an energy problem, then the energy problem has to be solved at least in part by society doing something. And that doesn't seem to be a terribly popular message, so it tends to not be one that is put out very much. So, conclusions then. Putting the power of computation into the hands of the masses has changed the face of computing. Again, it will do it again. I guess in another 10 years there'll be another breakthrough. Don't expect this to stop. I think it will. The details of its implementation will change, but the pace will continue. Electronic systems will become an essential part of our lives and of the economy. There's no way that we can choose not to pursue this, actually. If we don't pursue this, then actually society isn't capable of sustaining itself. So we have to do it. Power efficiency is a major issue then. Power efficiency has to be architected into the system and the hardware and the software right from the beginning to maximize the potential. It has to have indicators and levers. You can't do it without measurement. And to remember that moving data around is a major problem today. It's becoming a major problem today. It will be a major problem tomorrow. So, final word about ARM. What we actually do is help people to create these systems, to help them to get it right. Our methodology is primarily about hardware and software reuse methodologies, and it's based on a family of CPUs and GPUs. It's a simple thing really. It's a tip of an iceberg actually. Thank you for listening. I'll happily take any questions, but I'm aware of the